Yes, hello everyone. This is Benza Samuel from Group SW ML18, and we're covering a project on transfer learning and convolutional neural networks for automated EOS classification in unconstrained visual environments. So to proceed on, we have our contents for the presentation, that is for the introduction, the related work, problem statement, research questions and objectives. We have the research contributions, the methodology, the data description, the results, conclusions, then the limitations, the references, as well as the acknowledgement. When we look at the background of our research, it's mainly Uganda that has an an e-waste crisis of around 41 million tons. That was by the 2022. Then it has only 0.2 million tons. That is what has been recycled. Then we have no national recycling. That is where waste is just openly dumped. Existing computer vision models have failed in real dump sites. That is due to occlusion, weathering, and clutter. So the goal is to shift from dumping to urban mining. So proceeding to our related works, we have we have our we have our global e-waste having 62 million tons, that is by the 2023, which is most likely ICT devices, whereby Uganda with 40 million kilogram, that is for the 2022, then only 0.48% was formerly recycled. So managing the e-waste is kinda hard due to hazardous material, but most models are trained on clean lab images, that is images that are not real for African dump sites. So for the computational problem, because our problem was majorly talking of the domain problem and then the computational. But let me first talk about the domain. For the domain, we have huge mismatch that is between cleaning training environments and then the messy Ugandan scrapyards, whereby models fail in real life. Then for the computational, we have the off-the-shelf models that confuse the weathered, that is similar objects, that is for the shattered label, versus the damage damaged LCD, that is for the LCD monitors. So without robust transfer learning, that is for CNN, we cannot learn these invariant features. So when we proceed to our next bit of the presentation, the research questions and objectives, whereby we have what types of the e-waste objects are most common in Ugandan urban waste streams. Then the other question is how can the e-waste objects be accurately identified using the computer vision? Then the other question can be, what are the key challenges in deploying the automated waste classification that is in Uganda? Then for the objectives, we have to characterize the categories and volume trends of electronic waste generated in Uganda, to establish baseline data for automated identification systems. Then the other can be to develop a deep learning model for the automated identification and classification of e-waste components, that is from the digital images. Then we also have to evaluate the performance of the developed classification model with the existing waste management approaches, that is using the standard metrics such as accuracy, precision, then recall. Then we also have another objective of assessing the environment and public health risks that are associated with improperly managed e-waste. Identified Ugandan spots. So we have the research contributions. So these research contributions majorly look at the they majorly look at the characterized Kampala's e-waste, that is for the phones, the TVs, the computers that are 75 metrics tons over the 25 years. Then we also have the built the built deep learning framework, that is for the CNN, that is achieving a 99.5 accuracy. Then the deployed fast interaction, that was for the e-waste classifier, that is in Uganda, whereby we deployed it on Hugging Face. Then we also look at the quantified lead that is in soil, that is for some spots around certain areas in the country. Then when we look at the methodology, we have our stage one whereby we had the data collection, our stage two where we had pre-processing, our stage three for the model training, then we evaluated the model, then finally we had it deployed. So when we come to the dataset description and exploratory data analysis, that is for the EDA, we have something to do with the source for the datasets, whereby we mainly had our datasets gotten from Kaggle. Then we also have their links attached. I think that is part for the EDA. So when you go to the output, that is for the results that we had out of the models that we trained, that is specifically for the EDA. We have output results. So these normally present the experimental results that we had out of our project. That is using the figures, tables, graphs, as we can see. And majorly, we compare the model performance. That is also we had to show the confusion matrix, the row curves, and all the rest as we can see in the slides. Then we also had to look at the models majorly what we had for our project. Here on the models, we majorly looked at the FASTA CNN, that is a two-stage object detector that first proposes regions for interest, that is majorly for the what? That is majorly for the region proposal network that then classifies each region, and then it's accurate but a bit slow, as we found during the model training. Then we have the CNN, that is basic convolutional neural network for image classification, basically. That is for the LENet and the AlexNet. So when we go to the third model that we had in our work, that is for the model training, still around the models, we have our YLOV8. That one is a single stage real-time detector. It majorly divides images into grid and predicts bounding boxes and classes, that is in one pass. For it, it's a bit fast compared to faster CNN. Then we also had the binary classification. This output is one of the two classes. Sorry, it outputs what will go in for the two classes, that is for the eWest versus the non-eWest. Then we also have the multi-class classification. This output is one of the several eWest types, that is for the phone, laptop, the TVs, etc. Then when we come to still around the models, we have our efficient net BO. Sorry, efficient net B0, that is for still under the models, where we have a lightweight CNN that uses compound scaling. This achieves high accuracy with fewer parameters than the larger models. Then we also have the Dino V2, that is for the self-supervised vision transformer. This learns rich visual features from unlabeled images without human annotations. Then for the sum bit of it, still in the same model, this is Meta's segmentation model that can separate objects from background with zero shot or prompt-based segmentation. Then when we come to the 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 NNPU, that is still under the models, this basically is a method for learning from positive and unlabeled data. That is basically that. It is only limited to that, and it avoids it avoids trivial solutions by enforcing non-negative, and it's also useful when you cannot collect the non-EOS, that is for the images. So basically those are our models that we covered. So when we proceed to our model compression, we had three techniques whereby we had quantization, that is representing weights with fewer bits. So basically quantization is more of the bits, trying to reduce them in numbers so that we can compress our model. Then we also had pruning, where that is to do with removing unimportant connections. So that is also seen as as the architecture is seen below. Then we also had we had also knowledge distillation, where a small student model learns from a large teacher model. So basically that is what we had for our model compression. Then for the selected model architecture, we had basically the efficient net B0, that is basically what we chose. So among these models, while we used others like faster RCNN and also the YOLO V8. So when we come to the deployment pipeline, this majorly covers the movements of our model, that is from how we began from the user, finally back to how we deployed it, that is using our interface, the Hugging Face that we use for deployment. So when we look at the deployment pipeline, we have the model deployed as an interactive web app on Hugging Face Spaces, where users upload an image that model predicts. Then we have the EOS class. Then it returns the label and the confidence. So really when we have our deployment as below, we really had it cover the automated EOS classification that is in the unconstrained visual environments as we had our project state. So when we come to the demo, this is illustrating how our deployment went, where we have AI, waste classification and disposal assistant doing the image as it's first uploaded, then you can get to know whether it's metal, glass, plastic, or e-waste itself, and then it gives you a summary on what has come out of the model training. Then, as we conclude, we have something to do with transfer learning, that is for the efficient net, and then the yellow V8 that reduced training time, that is by around 2 times. Then this gives us an assurance that for the first Uganda Interactive EOS classifier deployed, it will aim to eliminate the lots of waste that has been disposed of improperly. So when we look at the limitations, that is still under the conclusion, but to the other side of it, we have data sets that are hard to access. Then we also had no local Ugandan data sets that took us to go on and use the cargo data sets, that is for deployment and training of the models, because we barely had Ugandan datasets that were available for us to use. Then we also experienced long training times, that is for some models. Then for our next steps, we we're trying to obtain, that is obtaining Ugandan-based datasets, that is also for the real-time deployment, and then optimization and then labeling data more specifically. That is for the next steps that we intend to take on. Then we also acknowledge the following resources and contributions that supported our research, that is for the cargo data sets, for the GitHub, then Hugging Face as well. I would like to end there. Thank you.